Good morning. Let's talk about the Diffie-Hellman exchange, asymmetric key cryptography developed by Mr. Diffie and Mr. Hellman. So how does this work? We can, basically me and Jeff, if we wanted to communicate and unlock private messages with each other, we can generate a shared secret key, right, that we never had to share across a public exchange so nobody can see it. How do we do this? We're going to use modular arithmetic, otherwise known as clock arithmetic, of two prime numbers. So we're going to use this equation in this example. X to the power of y mod z. Now the stipulation here is both x and z have to be prime numbers. Why? Because when you use prime numbers in this example as x and z, with modular arithmetic, you're going to have an equal probability of outcomes. So you can basically generate a random number. Okay, so what's modular arithmetic? And when you play around with this, you'll understand it a little better. If you just plug some different variables in. What we're going to use is 3 to the power of 7, my prime number, which is 2187, mod 17. So 2187 divided by 17 is 128. If we just wanted to put it 128 times, right, which is the nearest whole number that it goes in, our remainder would be 11. Okay, so 128 times 17, 2176. The difference between 2176 and 2187 is 811. So I'm going to go ahead and say, hey, I've chosen this private number. I'm not communicating this across the exchange because it's technically random to outsiders who see it. I'm going to say, hey, my public remainder is 11. He's going to say, okay, I'm going to choose a private number as well. That's awesome. Thank you for your help. 3 to the power of 12, so that's my private number. And I'm going to share you my remainder. Now what we can both do is do the same equation without even knowing it. It's just helpful because we have the first prime number. We have the answer, right? You don't need both prime numbers to do the same equation in this. Or you don't need both private keys. What we're both essentially doing is 3 to the power of 7 to the power of 12, or 3 to the power of 12 to the power of 7, okay? How are we doing this? I'm using his remainder to the power of my private number. He's using my remainder to the power of his private number. And what we both are going to get is the same number, because we're doing the same equation, which has generated a shared secret key, and we never had to tell each other 7 or 12. Okay, so I'm going to go ahead and upload this Excel document in the dropdown. If you want to play around with it, you can change these numbers, 7 and 12. In order to change these numbers, you can play with my little thing over here, my little proof, which is saying you need two prime numbers for there to be an equal probability outcome. Okay, hope you enjoy. Thanks.